Let's just wait for a few more minutes to see if Summer joins and then we'll begin. Let's begin. Hello everyone, this is Tanya. I'm one of the TAs assigned to the course Aircraft Design taught by Professor A.K. Ghosh. So today we'll go over the contents of week 6. Before that we'll go over the questions of week 5. Okay, so let's start. Is it taking a while to load? Yeah. The stability producing component for an aircraft is, we had seen this similar question earlier. So what is it? Is it the wing, fuselage, tail, or none of these? So if it's just a wing only configuration, let's just, so if you have the wing here and CG is somewhere here, right? So the wing is also an airfoil. So the wing produces lift, and if the aircraft is subjected to a gust, it pitches up. A vertical gust, it pitches up, right? And the wing produces a lift in the upward direction, and this contributes towards a pitch up motion towards the CG, about the CG, right? So it contributes towards destabilizing the gust effects. So it is not the stabilizing component, it's not wing, it's not fuselage either. What will produce a restoring moment? Some moment on this way, right? This way. So what is that? That is your tail, horizontal tail, right? So this produces a lift here, which produces a restoring moment, which counters the effects of the gust. Okay, so the correct answer is aircraft tail. Next, for a conventional aircraft, the sign of CL beta and CN beta respectively. This again we have seen multiple times. What is the right answer? So CL beta, let's just look at the slides that we've gone over before. So these are the equations for lateral stability and control. We initially discussed the conventions. We did this last week. Then we discussed the only criteria for static lateral stability is that CL beta should be less than 0 when the aircraft is subjected to a positive gust. What is a positive gust? Positive side slip. So this is your fuselage reference line. This angle. If your relative velocity is on the right of the fuselage, then it is positive beta. Okay, this is positive beta. So when the aircraft is subjected to positive side slip, the restoring moment, the moment that's required is positive CL, right? C small l, rolling moment should be positive. Excuse me. Okay, so for a positive beta, you need a negative, oh sorry, I think I made a mistake. For a positive beta, you need a negative CL. dCl by d beta should be less than 0. Okay, so this is the only criteria for lateral stability. So the first one, this will be negative. Now Cn beta. It's for directional stability. Okay, so again we went over the conventions, and the only condition for static directional stability is that Cn beta should be greater than 0. So for a positive beta, your Cn should be positive. Okay, so this is your only condition. dCn by d beta should be greater than 0. So this should be positive. So what is the right answer? The third one. Okay. Next question. The rudder control effectiveness depends mainly upon, what would it be? Is the lift curve slope of the vertical tail, of the fuselage tail, of the wing, or none of these? Where is the rudder located? Where is the rudder located? On the vertical tail. So it will be the lift curve slope of the vertical tail, right? So these were the equations for directional stability and control. And your control rudder effectiveness, Cn delta R, this one. It depends upon efficiency of the vertical tail, volume of the vertical tail, Cy beta. What is Cy beta? It is the lift curve slope of the vertical tail, right? Why does it say Y? Because it's producing force or lift in the Y direction, right? So Cy beta, it depends upon the lift curve slope of the vertical tail. Okay. The contribution of vertical tail towards lateral stability mainly depends upon, we just discussed this. What is the right answer? Just the previous question we had seen the equation. What would the right answer be? So what was the equation? Look at the equation now. Can you tell me? Look at the question again. Vertical tail, contribution of vertical tail towards lateral stability depends mainly upon. It has both the vertical tail volume ratio and efficiency factor, right? It has efficiency factor and volume ratio. So it is both, correct? Okay. Which placement of wing has least lateral stability? This question we have dealt with multiple times. Which is the right answer? And can somebody justify the answer? So low wing is the right answer. Why does it have least lateral stability? So if it's a high wing configuration, we have seen this multiple times. And then when it rolls, the oncoming velocity will impinge on the wing in such a fashion such that it produces a restoring moment. Now if it's a low wing and it rolls in the same direction, the oncoming velocity impinges on the wing in the reverse fashion, okay, and it produces a further destabilizing moment. It goes further in the direction of the roll, so there is no restoring moment, right? So low wing does not produce any lateral stability. All right, so right answer is low wing. It has the least lateral stability. What function does an aircraft spar serve? What is a spar? What is a spar? Let's look at the diagram of the wing. So you can see several components here. So the spar is the structure that goes along the length of the wing, right? Along the span of the wing. So this is your spar, correct? So now can you tell me what is the function of the spar? Does it carry the flight loads, wing loads, or both of these, or none of these? Carries both flight loads and wing loads, right? It carries both of loads, flight loads and wing loads. So I think I have a slide somewhere here. Yeah. So the forces acting on the wing spar, you have an upward bending load that is resulting from the lift that is acting on the wing during flight, right? So there is a lift force generated upwards. So then you have an upward bending moment, bending load on the spar, because spar is along the span. Similarly, when it's on the ground, when it's not in flying condition, due to the weight of the structures and weight of all components on the wing, it produces a downward bending moment, right? Then you have drag loads when during flight, depending on the airspeed and inertia. Then you have twisting loads. Twisting loads, why? Because the angle of attack throughout the span of the wing is not uniform. It can be uniform, but then you have introduced washout. Washout was what? Wash in, wash out. We had dealt with this. Remember, it's the slight twist of the wing tip from the wing root. So the wing setting angle at the root and the tail, root and the tip are different, right? So that is wash in or wash out. Due to this and due to other factors, the angle of attack along the span of the wing would not be the same, right? It will keep changing, and hence you will have different twisting loads acting on the wing. And since the spar runs along the length of the wing, along the span of the wing, it is subjected to twisting loads. So it is subjected to both structural and flight loads, right? So the right answer is both flight loads and structural loads. So that is wing loads. Okay. The use of dorsal fin in aircraft design is this similar question we had seen in the last class. What is a dorsal fin? I think a couple of weeks back we had seen something related to dorsal fin. So what are dorsal fins? Can someone tell me what dorsal fins are? Okay. So if this were your side view, there is a structure placed here, right? So that is your dorsal fin. And we had seen when this is used, why this is used, what all aircrafts have it, right? So why is it used? To improve directional stability, correct? To improve directional stability. It's mostly used when the aircraft encounters high side slip events, right? So what happens is that it increases the area, increases the range of the side slip that the aircraft is able to tolerate, or the aircraft is able to negate, right? When it encounters side slip angle, the aircraft, a stable aircraft, has the inherent tendency to negate the effects of the side slip. So this dorsal fin increases the range up to which you can negate the effect of side slip. So it improves the control effectiveness of the vertical tail. So it improves directional stability. What function does the aircraft rib serve? What was a rib? Look at this figure. We're coming back to the same figure. So the rib is perpendicular to the spars, correct? So they are the chordwise direction of the wing along the chord section. Okay, so those are spars. They're perpendicular to the those are ribs. Those are perpendicular to the spars. Now, tell me, what function does the aircraft rib serve? They're all of these, right? So they are stringers to the wing spars, they support the structure, they also enable load transfer. So it's all of these. Okay. Among the following, which aircraft has a ventral fin? Okay, can you quickly just Google these aircrafts and see which of those have ventral? What are ventral fins? So dorsal fin was, bear with my drawing. So this was the dorsal fin on the upper surface, right? Below, something here, something like this, that would be a ventral fin. This is very similar to the structure of a fish, okay? Both are streamlined bodies and both have these fins. So yeah, just Google these aircrafts and see which of them have this ventral fin. This is ventral fin. Okay, so that is the ventral fin. Just Google these, look at the images and tell me which ones have ventral fin. Just take a couple of minutes. Could you look at the aircrafts? Which ones have ventral fin? Okay, let's look at the images. So yes, the first one is the MiG-23, right? The first one is the MiG-23. It has a ventral fin. You can see it's here, right? So the MiG-23 has a ventral fin. Next is the Beechcraft Duke, which is this aircraft here. So this is 1, this is 2, and this is 3. So here also, if you look closely, there is a ventral fin, correct? So the Beechcraft Duke also has a ventral fin. Third one is the Bush Caddy. Here again, you have the ventral fin. So all three aircrafts have the ventral fin. Right, so answer is all these, right? All of them have ventral fin. Okay. Next, what is the use of a ventral fin? What do you think is the use of a ventral fin? What is the use of ventral fin? Provides a yaw damping, right? So it is to prevent yaw. It is not to prevent yaw as such. It is to provide a damping towards the undesirable yaw during a spin. So if it has this ventral fin, then it can recover from the spin. Okay. Okay. Now I think I had asked this question last class or something. We'd seen anhedral angles. Dihedral angle we know. What was dihedral angle? So if this was a low wing, it's usually seen with a dihedral angle to improve lateral stability. So what is anhedral and why anhedral? So where is the anhedral seen? What kinds of aircrafts do you see the anhedral? Just look it up quickly. Just go to Google and see what kinds of aircraft have the anhedral. What kinds? General category. So two types of aircraft in general. It's the cargo aircrafts and the fighter jets, right? Both these aircrafts are seen with the anhedral angle. What is an anhedral angle? Oops. So, where were we? So if you have a high wing, it is generally seen with an anhedral, right? So, okay, so in terms of lateral stability, the low wing is unstable, right? So laterally unstable. Now when you give it a dihedral angle, when you give a dihedral angle to the low wing aircraft, it becomes laterally stable, more laterally stable, okay? Laterally stable. Now your high wing is inherently stable, lateral wise. So laterally stable. So now can you try and tell me what the anhedral angle does? What does the anhedral do? So this is just the dihedral angle. This is same representation for anhedral but just like negative. So what does the anhedral do? Just look at these images and tell me what the anhedral does. What does the anhedral angle do? So it introduces some amount. So if the aircraft is very stable, right? Excuse me. If the aircraft is very stable, it becomes very difficult to control it or maneuver it. As the stability increases, controllability reduces, right? So for cargo aircraft and fighter jets, you need to have some more amount of controllability. So what the anhedral angle does is to slightly reduce the stability. So it does reverse than what a dihedral angle does. The anhedral slightly reduces the stability that is inherent to the high wing. Okay, so high wing and dihedral, both of them contribute towards roll stability, and hedral contributes towards roll instability. It reduces the stability slightly. Okay, I just thought we should know this. Okay, then we had seen adverse yaw, I think a couple of weeks ago. So what was that? That it was introducing a rolling moment introduced a yaw. So when you rolled right, you yawed left, which is undesirable. That was adverse yaw. Similarly, you have a side slip induced rolling moment. Why do you think this happens? Can you think about some reasons why the side slip induces rolling moment? When the aircraft is encountering a side slip, it's a positive side slip, and if it's a stable aircraft, it tends to yaw towards the right and negate the effects, right? So when side slip is there, it yaws right. Now what do you think contributes towards generating rolling moment due to side slip? So now let's just see this. So this is the vertical tail, okay? So when there is a side slip angle, it produces a force Fy. So is this positive or negative, Fy? The force that you see here, is it positive or negative? So your positive y-axis is in this direction, right? So this is your positive y-axis. So Fy is negative, correct? And it produces a rolling moment, a yawing moment, right? Produces yawing moment that negates the effect of beta. Well and good. Now why does it produce a rolling moment? Can you look at this force Fy and tell me why it produces a rolling moment? Why does it produce a rolling moment? This negative Fy, why does it produce a rolling moment? So when you see it from the side view, okay, so you have, this is your, so you have Fy and Cg is somewhere here. So why does it produce a rolling moment? Why does it produce a rolling moment? The force Fy, why does it produce a rolling moment? We understood why it produces a yawing moment. Why does it produce a rolling moment? So when the force is acting above the Cg, it produces a rolling moment. If this is your x-axis, it produces a rolling moment, right? This is one of the reasons why the rolling moment, side slip introduces the rolling moment. Let's look at the other. Oops. Okay. Let me just erase this. Okay. So the dihedral angle of the wing increases the local angle of attack on the windward wing. Correct? Dihedral angle of the wing increases the local angle of attack on the windward wing, and this produces a rolling moment. So there is a change in the lift produced on the windward wing and the leeward wing, right? So then there is a rolling moment because the lift on one wing is more, lift on the other wing is different. Another reason is the sweep angle of the wing. Similarly, because of the sweep angle of the wing, the lift produced on the two wings, on the windward and the leeward wing, would be different, the normal component, right? normal component would be different, and hence the lift produced would be different, and hence it will introduce a rolling moment. Then cross flow around the fuselage. I think I have an image for this. We'll just get back to that. This is what we just saw, the location of vertical tail in relation to the location of center of gravity. So that is this what we had discussed initially. Now cross flow around the fuselage. Yeah. So now that it's loaded, around the fuselage, due to the low and high wing, both those wings, it produces a rolling moment because of the cross flow around the fuselage. You can see it here. So again, there is a difference in angle of attack on the windward and the leeward side, and this depends on the positioning of the wing, high wing or low wing, right? So this also produces a rolling moment. So these are the several factors which contribute towards producing a rolling moment when the aircraft encounters a side slip. Okay. Now let's look at a few questions which pertain to week 6. Which of the following statements are true for a typical flight profile for quad rotor and fixed wing aircraft? We had seen this, right? We had seen this question I think in week 3 or 2. So for a quad rotor, which one is the right answer? Which one is the right answer? Try to figure it, try to give a reasoning. So the first one is the right answer. Why? So for a quad rotor, for a fixed wing, you know why the thrust to weight fixed wing? Fixed wing, thrust to weight ratio. Oops. Fixed wing thrust to weight ratio will be less than 1 because thrust is not the component that produces the that balances the weight. What is the component that balances weight? It's lift, right? So lift to weight ratio is what we see there. Now for a quad rotor, you have thrust to weight ratio greater than 1 and equal to 1. So if the thrust to weight ratio is equal to 1 for a quad rotor, what is that condition called? It's when it's hovering, right? Hovering. And if it's greater than 1, it's for the climbs and the takeoff. Okay, now let's look at the next question. Okay. For two different aircraft, a motor glider and a surveillance aircraft, the PS to W ratio and L by D ratio are given below, where PS is shaft power. For a steady climb at speed of 100 km per hour and propeller efficiency of 0.8, rate of climb of both the configurations are. So we need to find out rate of climb. And note that the unit of velocity is kilometer per hour. So try doing this question. You have to find the rate of climb. Just write down the equation for rate of climb and you should be able to do it. Okay? Just try doing it, take a couple of minutes and then we'll solve it together. Okay, have you tried solving this? What is the equation for rate of climb? So what was the equation for rate of climb? Rate of climb is power available minus power required by weight. So here, what is power available? They've given you the shaft power to weight ratio. So what do you think power available is? Power available is shaft power into efficiency, right? So let's just calculate that. Okay, now if we substitute it here, power available is PS into eta S by W minus what is power required? What is power required? Power required is thrust required into velocity, right? So thrust required into V infinity by W. What is thrust required? If you take steady level, they've said use small angle assumption, so you can assume a steady level flight. So what is thrust required? So for a steady level flight, thrust required is drag, right? Just substitute it there and tell me what the answer is. So you can just substitute all these values. So it will just be PS eta S W by thrust required is drag. So what happens here? It becomes V infinity CL by CD, right? L by D. CL by CD or L by D. So now just substitute the values and tell me the answer. PS by W is for each of those cases. So 7 eta S is 0.8 minus V infinity is in kilometer per hour. Make sure you convert it to meter per second. 100 into 1000 by 3600 and L by D is 12. Correct? So now what is this answer? Just let me know the answer quickly. For both the cases, do the same thing for the other case, for the surveillance drone. It's not, oh, it's 1 by 30. Correct. So what is the answer? Do the same thing for the other surveillance drone and then tell me the answer. I haven't calculated it, so just let me try calculating. Where 4.67, right? I'm getting 4.6741. This is the right answer, but just calculate it for the surveillance drone as well. The same formula, just substitute those corresponding values. Yeah, so you are getting 6.822, right? So that is the right answer. Let's go to the next case. Just a minute. Okay. For a propeller aircraft, the maximum range, for a propeller aircraft at maximum range, what will be the wing loading given CD naught, aspect ratio, Oswald's efficiency factor, and dynamic pressure Q? So they've asked you to find out. Oops. Wing loading. This is what you're supposed to find out. Can you try doing this? Concentrate that it's given maximum range and it's a propeller aircraft. So I think we'd seen these relations in the first couple of lectures. Let's try doing this question, then we'll solve it together. have you been able to do this? Okay, let's just do it together. For the maximum range condition for a propeller aircraft, what is CL? What is the CL here? We had seen this in the couple of lectures right in the beginning, right? So it is root of CD naught by K. So what will it be here? It will be root of 0.02 by K is 1 by pi EAR by R. What is this value? Just calculate it. I haven't calculated it. Let me just try it. So it comes to 0.55. Now they've asked you to find out wing loading. What relation do we know? We know lift equal to half rho v square SCL. Lift equal to weight, we can make that approximation. From here you can calculate wing loading. So what is W by S? It is half rho v square CL, and half rho v square is Q. So you have Q CL. Q is 39.2 Pascal. CL is what we have found out, 0.55. What is this value? It is 21.5, right? That is the wing loading. Okay. Okay. Yeah. So these were the formulae that we used for the maximum range of a propeller-driven aircraft. It is this. This is what we used. Okay. Next question. What should be the load factor if lift coefficient is designed as 2.1? So they've given you CL is 2.1. Dynamic pressure Q is 20 Pascal, similar to the previous question, and they've given you wing loading 12. They've asked you to find out load factor. Slightly different from the previous question. Try doing it. Quickly do this. We'll do it together. Just do it quickly. So it's very similar to the previous question. How do we proceed? Can someone tell me? Okay, here since the load factors come into play, what it means is that L is equal to NW. So load factor is the ratio between lift and weight, right? So now when you write the formula, what happens is, so you have lift is equal to NW, lift equals NW equals half rho V square SCL, correct? And then you take out, you need to find out load factor N. That is nothing but Q by W by S into CL, correct? So try doing this. So substitute the values. Q is 20, CL is 2.1, W by S is 12. So what is the answer? Just substitute the values and tell me. Comes to 3.5, right? So that is the answer. Now look at the next question. What is meant by airborne distance? The distance between takeoff point and the point at which the screen height is cleared. The distance between liftoff point and the point at which the screen height is not cleared. Distance between liftoff point and the point at which the screen height is cleared. Distance between takeoff point and the point at which screen height is not cleared. What is screen height? So it's the height that is specified that of an imaginary obstacle that you have to clear during takeoff. Okay, so let's just look at the figure. So yeah, so this 35 feet that you see here is the fixed height, which is what is given. It's a fixed height that the aircraft has to clear. This is just a clearance given so that it does not encounter any difficulties during takeoff. Okay, so here the screen height is 35, like that is what is given for a commercial aircraft, 35 feet. Now let's look at the different speeds. What is, it starts with V equal to 0. What is Vs? The first speed that it has to clear is Vs. What is Vs? Vs is stall speed, right? Stall speed. So it has to be, the velocity has to be higher than the stall speed. Next, what is stall speed? What is stall? What is stall? Okay, we've discussed this several times, so if anybody has a question, do ask me, but otherwise we'll move on. Next is VMC. What is VMC? What is that velocity? Minimum control, velocity of minimum control. Minimum control, what does it mean? What is velocity minimum control? Whether rudder becomes effective, right? So if an engine, it's also defined as if an engine were to fail, it is the minimum velocity at which the aircraft should be flying for the rudder to compensate the failure of one engine, or it's the minimum velocity at which the rudders become effective. Okay, okay. Next is V1. What is this V1? What is V1? Decision speed. So what is the decision speed? It is the speed which is sufficient for a takeoff. It is also sufficient for the pilot to abort the takeoff. Okay, so it is the speed that is sufficient for both. It is just sufficient for takeoff and just sufficient for aborting the takeoff. Okay, so this is the point at which he needs to make that decision. Next is VR. What is VR? What is VR? R is for rotate. It's the velocity at which you deflect the elevators and the aircraft starts pitching up, aircraft starts rotating. Okay, that is V rotate. Next is VMU. What is VMU? VMU and V liftoff. What are these? So this is minimum unstick. MU is minimum unstick. V liftoff is V minimum unstick is the velocity that's required for takeoff, and V liftoff is just slightly more than that, such that the undercarriage does not brush the surface. Does not there is enough clearance for the undercarriage to lift off without brushing the surface. Okay, so that is that liftoff VMU and VDF. What is V2? V2 V1 was decision speed, so V2 is something similar. What is V2? It is the speed at which even if one engine fails, there is sufficient velocity to clear the screen height. Yes? Okay, so that is that. So the question was, what is meant by airborne distance? So what is the right answer? Distance between liftoff point and the point at which the screen height is clear, right? This one, this distance. Okay, next question. The total takeoff distance is it A, airborne distance, B, ground run distance, or both of them, or the difference of these two? It is the sum of the airborne distance and the ground run distance, right? It's this whole thing, the whole profile, the ground roll and the takeoff distance, airborne distance, right? So the whole thing is the takeoff distance, sum of A and B. Which of the following is not a type of flaps used in aircraft? So what are flaps? Right answer is dorsal flaps. You have dorsal fins, but no dorsal flaps. Plain flap, slotted flap, follow flap, they are all types of flaps. Dorsal flap is not a flap. Dorsal fins exist. Okay, so what are flaps? What flaps are high lift devices. So you have flap, which is high lift device. High lift device. What is high lift device? It increases your CL max. When do we have to use this? During takeoff and landing. So this is used during takeoff and landing. Okay, so it's a high lift device that is deployed during takeoff and landing to increase your lift. So your cross section of the wing and the tail wing it has some certain design CL and design CL max, but you want it to be more during takeoffs, right? So at that time you deploy this flap, you deflect it or deploy it depending on the type of flap, and it provides you with greater lift. Okay, so now let's just look at the different types of flaps. Okay, before that, dorsal fin, right? So dorsal flap is not a type of flap, it's a type of fin. What did the fin do? It was something like this. So this is your typical aircraft side profile, and this triangular portion, which is present in some of the aircrafts, they give you an extra range of side slip for which the aircraft will still be stable. Okay, so this is only used in when the aircraft encounters high side slip situations. Okay, so this is the dorsal fin. I think we had seen one question right in the beginning. Let's get to that. We had seen this a couple of weeks ago also, and today in the beginning one question dealt with ventral fin, one question dealt with yes, the use of dorsal fin in aircraft design. So what the dorsal fin does is not provide directional stability, it improves the directional stability. Okay, that's in high side slip situations. Yeah. So now let's get back to the different types of flaps. The plain flap is one just that similar to a control surface where it deflects. What it does here is it increases the camber. When it increases the camber, you get greater lift. It's effectively increasing the camber. But what is the problem with this? It effectively increases the lift, but it also increases drag. Correspondingly, it increases drag also. Okay. So next we have a type called split flap. What is the benefit of split flap above plain flap? Benefit is that in the case of plain flap, there is a possibility of boundary-less separation at this point, right? So there's a sudden change in camber and there's a possibility of boundary-less separation. In the case of split flap, because only the bottom surface is deflecting, the boundary layer above the surface of the flap or the wing continues to remain attached to the surface. Right? So there is lesser possibility of boundary layer separation. Then you have something known as slotted flap. What is the benefit of this is that if there is a gap between the flap and the main body, or the hinge, right? So there is a gap there. What happens is that the airflow passes through this gap and it re-energizes the flow above the surface of the wing, ensuring the boundary layer sticks on for larger time. So there is again lesser possibility of boundary layer separation. Okay. Then you have something known as the Fowler flap. Fowler flap is where it's a split flap that comes out and then deflects downwards. What is the benefit of this? How is it different from split flap, plain flap, or what is the benefit, or what is different? All these flaps, they increase the camber, they change the camber, effectively change the camber. What is Fowler flap? How is that different? Here it also changes the chord. It's not just the camber plus chord, both are changed here. Similarly, you have something known as double slotted Fowler flap, and it goes on so on and so forth. Well, you have several pieces on the Fowler and you're getting a greater degree of control over how much camber and chord you want to change. Okay. Next, let's look at this question. An aircraft is cruising with a lift coefficient of 2.5. So CL is 2.5. Thrust loading of 0.6. So that is T by W 0.6. Find the drag coefficient of the aircraft. They've asked you to find CD. Okay, let's take a minute or two to try doing this on your own, and then we can do it together. They've asked you to find the drag coefficient of the aircraft given your lift coefficient, thrust loading. This is fairly simple. It's from the concepts of week 6, but we are also seeing this in the initial couple of weeks. Just write down the formula for a thrust loading or a steady level flight, and then you'll be able to do it. Some issue with the internet, I think. Okay. And let's just try doing this. Am I audible? Okay, so let's proceed with this question. The equation for steady flow is lift equal to weight, thrust equal to drag, and then when you divide this thrust equal to drag by the above equation, when you divide them, you get thrust by weight equals d by L, or 1 by L by d. Okay, So just substitute these values and then you will be able to find out CD. This is just 1 by CL by CD. Okay, so thrust loading is, so just write the equation for CD. It is thrust loading, just manipulate this equation and then you get this. So thrust loading is 0.6 and CL is 2.5. Multiply this to get the answer of CD. CD is, let me just multiply it. 1.5. Okay, correct me if I'm going wrong, but the answer is 1.5. Okay. So next question. For an aircraft in flight, the wings produce a lift of 25,000 Newton. So lift is 25,000 Newton. Drag of the aircraft is 1 order of magnitude smaller than the lift. Find the jet engine's output for a steady flight at 500 km per hour. Again, note that the unit is kilometer per hour. Okay, so velocity is 500 km per hour. So this is second time that is in today's questions that we are encountering the units that are different. So just keep an eye out for that. Excuse me. Okay, so here they've asked you to find out jet engine's output. What is the jet engine's output? Jet engine's output is thrust, right? So it's thrust. But look at the answers. The options are given in megawatts. So the output would be power. We need to find out power. How do we find out power? What is the formula for power? Just try doing this. They've given you lift, they've given you drag. How much is the drag? 1 order of magnitude less than the lift. So how much is the drag? It will just be 2500, 2500 Newton. Okay. So now you just have to find out power in megawatts. Take a couple of minutes to try solving it and then we'll do it together. It's fairly simple, right? So you just have to find the power. You able to do this? Can you think about how to do it? Power, what is the formula for power? Jet engine's output is thrust, but we need to represent it in terms of power. So that is the clue. let's try doing this. So the power is nothing but thrust into velocity, right? So P is T into velocity. Velocity is given to you, correct? How do you find out T? For steady level flight, what is T? T is nothing but drag, correct? For steady level flight. So you just have to put in 2500, which is drag, into velocity. Velocity is 500, but it is in kilometers per hour. We need to convert it to meter per second. So just multiply it by 1000 divided by 3600. So what is the answer? Just calculate this. I haven't calculated it. Point 347. Right? In megawatts, so it's about 0.35 megawatts. Okay, just keep the units in mind when you try doing these questions. Okay, next question. For a transport aircraft, the maximum allowable load factor is 6. What is given? Nmax. Nmax is 6. Find the thrust loading if the aspect ratio, Oswald's efficiency factor, and CD naught are given. They've asked you to find out thrust loading. How do we do this? Again, just take a couple of minutes, think about it, and then we'll try solving it together. It should be fairly simple, but just concentrate on the maximum allowable load factor. That is the key word here. So it's max. Try doing this, and then we'll do it together. Just take a couple of minutes, think about it. Think about what load factor is, what is the formula, and try equating it using the things that are given to you in the question. And keep in mind that it's the maximum load factor that is given to you. What is the formula for load factor? Load factor is L by W, correct? So just manipulate these terms to get the quantities that you have given in the question. So if I were to open or split this equation, it will come to T by W, right? It's just how it's seen in the previous question, L by D, correct? Okay. So now in the question they've given you N max, not just N, it's maximum load factor. So that would be T by W into L by D. T by W into L by D. And it says maximum load factor, so both these quantities have to be maximum. This has to be maximum, this has to be maximum, right? So I hope this gives you a clue. Try solving it now. We need to find out T by W, max or T by W, thrust loading. Okay, let's just try doing this. So they've asked you to find thrust loading. So if I just rearrange these terms, what do we get? We get N max into 1 by L by D max. Now how do we find L by D max? So just take this. So CL at L by D max. What was the formula? It was under root, we just saw this, under root CD naught by K. So just substitute the value. CD naught is 0.01, K is 1 by pi, AR is 8.5. So what is this value? Just calculate and tell me. I haven't calculated it, so let me try doing it. Getting 0.432. What about CD at L by D max? You just have to put in the drag polar equation, that is CD naught plus KCL square, or in the case of L by D max it is 2 CD naught. Calculate this value, which is 0.02. So now plug it in here. N max is 6 into 1 by L by D max. So L by D max is nothing but CL by CD max, right? Let's put it in there. So you have L by D, that is 0.432 by 0.02. So what is this value? Just calculate and let me know. I'm getting 0.277. Right, so this is the right answer. I hope this was clear. Let's move on. Okay, so this was a question that we had seen in the last class. So it's not from your assignments. It's just something that I thought we should know. We had done it for a simple case last time, and this is for a more complex structure. Since a lot of people aren't here today, let's just keep this for the next class because it's something that we should do through a discussion, and I don't think we have sufficient time to complete the whole thing, but try doing this again. Find out the neutral point. So we had done aerodynamic center calculation followed by neutral point calculation for a simple structure, that is a wing and tail. Now here you have two wings, one tail and one canard, okay, and they've given you different distances between each section. You just have to find out the neutral point. So find out the neutral point first, and then we'll look at this table, which is the aerodynamic center. Get it in terms of find the neutral point in terms of like names. Okay, so this can be, if this is your leading edge, right, so this can be XAC wing, and if this is the wing, you have XAC canard, and then you have XCG, and then you have XAC tail. Okay, in terms of these names, try finding the neutral point. At least try to find the neutral point. So just find XNP or XNP bar equation. Okay, just find the equation for XNP bar. I hope that can be done, and then we'll meet next week and we'll solve this completely. Okay, so I hope this session was clear today. Any questions from today's session? It was week 5 assignments and contents of week 6. I hope it's clear. If not, put up your questions on the forum. We'll try to answer them, or if not, we'll meet again next coming Tuesday. Okay, so thank you. We'll meet on Tuesday.